In Fermi-Dirac statistics, we have seen the several important applications of this statistics. We have calculated the electronic specific heat, okay, and so many other applications. Actually, the most important and interesting application of Fermi-Dirac statistics is the white dwarf stars. When you say white dwarf stars, actually these are the stars which are much fainter. Name is white dwarf, but it is not a bright star, it is much fainter. And it possesses a smaller diameter and very dense. Its density is very high. You will see that its density is almost 10 times more than the density of our sun. Okay? So, its diameter is small. When you say, it means when you will compare the diameter of these white dwarfs with other stars of same mass, then it is found that diameter of this star is lesser than those stars actually. Okay. In fact, you know, the stars has an evolution. It is produced, it grows, and it dies. Okay. So the white dwarfs are also an outcome of the stellar evolution. Okay. You know, it is an established fact that the source of an enormous amount of energy of a star is the continuous process of fusion taking place inside the star of hydrogen to form helium. Actually, almost all stars give you energy, give light. How? What is the actual process? You know it very well that every star is made up of hydrogen. And due to the large temperature inside the core of the star, the process of nuclear fusion of hydrogen takes place, and hydrogen continuously is converted into helium. And in that very process, an enormous amount of energy is produced. Okay? And that's why the cause of the enormous amount of energy from a star is the process of fusion taking place inside the star. Okay? Actually, during the process of continuous fusion inside the star, the outward pressure generated is so great that it outbalances the inward gravitational force. Okay? In this process, the outward pressure is much more greater than the inward gravitational force. So, as a whole, the stars get expanded, or you can say that consequently the star continuously expands till it consumes much of its nuclear fuel, and a star of this type is known as red giant. Okay. So in this way a red giant is evolved. Actually, when the nuclear fuel is completely used up, the outward pressure is not sufficient enough to balance the inward gravitational force. Okay? And in this condition, the stars begin to collapse under its own gravitational force. And finally, they reach in a stage which are known as white dwarfs. Okay? Actually, the density at this stage becomes so great that it gives rise to an effective pressure strong enough to prevent further contraction. Actually, when further contraction will take place, Polish exclusion principle will be actually violated, and actually after that the contraction is prevented by the effective pressure, and in this way an equilibrium situation is established when this star is formed. Okay. So many such white dwarfs have been observed in our universe. Okay. When you talk about some typical properties or typical specifications or data regarding this white dwarf, you can see uh, when it is actually most important for the objective type of question. When you will ask that what is the content of a white dwarf? A white dwarf is made up of hydrogen or helium. Answer will be helium. Although you know every star is composed of hydrogen. Basically, these white dwarfs are also composed of hydrogen. But you know, due to the continuous fusion process inside the core of this star, the hydrogen fuel is completely exhausted, and actually that is converted into helium. So the basic constituent or content of this star is not hydrogen but helium. Okay. When you talk about the mass of this star, it is of the order of 10 to the power 30 kg. This is just an order. For example, if you talk about a very important white dwarf known as Sirius B, its mass is 2.09 into 10 to the power 30 kg. So this is order, something will be multiplied. And you know, mass of our sun is also of this order. So mass of this white dwarf is of the order of mass of the sun. When you talk about the density of this white dwarf, the density of its material is all of the order of 10 to the power 10 kg per meter cube, which is almost 10 times of the density of sun. Okay. And the temperature of the core or the central region of this white dwarf is of the order of 10 to the power 7 Kelvin. And you know, the temperature of the core of sun is also of this order. So the temperature of white dwarf in its central region is almost same as that of the temperature of sun. Okay. And its radius is of the order of 10 to the power 3 kilometer. This is just an object. When you talk about this Sirius B, which is a good example of white dwarf star, then its radius is 5.57 into 10 to the power 3 kilometers. So this is order. Okay. So these are some important specifications or data regarding this white dwarf. Okay. Actually, a detailed study of the constitution of white dwarf stars reveals that they lack brightness. This is a very important fact. Name is white dwarf, and when a question, objective question will be asked to you that white dwarf is a bright star, answer will be no. It lacks brightness. Okay. White lacks brightness. The reason is that the hydrogen contents are more or less used up in this star. Okay. They are composed mostly of helium, as I have told you. So whenever light brightness, whatever the light brightness they have, it is derived from the gravitational energy, which is released through a slow contraction of the star. Okay. So this star actually lacks brightness. Actually, this fact I have mentioned here, you can see. Okay. Now we will see the basic theory of these white dwarfs. Actually, we will see that applying the Fermi Dirac statistics, we can explain the important properties of this white dwarf star. Okay. Actually, as I have told you, that an idealized model of white dwarf star may have the central temperature of the order of 10 to the power 7 Kelvin. You have seen, okay? Actually, which corresponds the mean thermal energy of the order of 10 to the power 3 electron volt. Okay? If you will take T equal to this much, then KT will be of this order. Okay? Hence, the helium atoms are expected to completely ionized at this much temperature or this much thermal energy. Definitely the helium atoms will be completely ionized. Okay? And so the white dwarf star may be regarded as a gas composed of helium nuclei and electrons. Okay? Helium nuclei and electrons, because at this much temperature helium atoms will be ionized. So you can think that the core of this white dwarf star contains the nuclei of helium and electrons. Okay? Actually, in this way you can say that white dwarf star may be regarded as a gas composed of helium nuclei and electron as well as radiation. However, we may neglect the pressure of the helium nuclei and radiation in the system and regard the star as a gas of electrons with density of the order of 10 to the power 36 electrons per meter cube. Okay? And since it is just a gas of electrons, and you know electrons are fermions, they obey Fermi Dirac statistics. So definitely this gas will obey Fermi Dirac statistics. And that's why applying the FD statistics we can analyze the theory of white dwarfs. Okay? Now for developing the theory of white dwarf, first of all let us find the Fermi energy first of all. You can remember I have provided a separate video on free electron theory of metals on Fermi energy, and definitely I have told you in that video that you must remember this result for your further concept. So if you denote this Fermi energy by the symbol epsilon F, then it is given by the expression h square over 2m times 3n divided by 8 pi whole to the power 2 by 3. Here, you know, h is Planck's constant, m is mass of electron, okay? And what is this n? You know, n is capital N over V, where capital N represents the total number of electrons and V is the volume. So this small n represents the number of electrons per unit volume, which is of the order of 10 to the power 36 in this case. So when you will substitute n equal to this 10 to the power 36 and other h and m are universal constants, then after simplification you find that the Fermi energy is almost equal to 20 mega electron volt. Okay? This is the value of Fermi energy in this case. Now, after knowing this Fermi energy, we can easily find what will be the Fermi temperature. How Fermi temperature is defined, you have also learned in my previous video. You know, if Tf is the Fermi temperature, then it is defined as epsilon F divided by K, where epsilon F is Fermi energy. When you divide the Fermi energy by the universal constant K, which is Boltzmann constant, then you get the Fermi temperature. Here you have seen that this Fermi energy is 20 mega electron volt, and when you will convert this Fermi energy into joule, you have to multiply it by 1.6 into 10 to the power minus 13. Okay, and the value of K is 1.38 into 10 to the power minus 23. Okay, joule per Kelvin. So after simplification we get that in this case the Fermi temperature is 10 to the power 11 Kelvin, which is a very large temperature. Okay, you know that temperature of the central region of this star is 10 to the power 7 Kelvin, and the Fermi temperature corresponding to it is 10 to the power 11 Kelvin. So when you will find Tf over T, this will be 10 to the power 4, which is much greater than 1. This is much greater than 1. Actually, when this Fermi temperature is much greater than the central temperature, what this value actually refers? Actually, this larger value of Fermi temperature implies that electron gas is highly degenerate. When you say that this is highly degenerate, it means we can regard the electron gas to be an ideal Fermi gas in a state of almost complete degeneracy. When you say complete degeneracy, that means it is in its ground state. Okay, and as another important fact, as you can see that electron density is 10 to the power 36 electron per meter. It is also very large. So the Fermi momentum Pf will be comparable to m naught c, where m naught is the rest mass of the electron and c is a speed of light in free space. Okay, and so the dynamics of the electrons in this case will be relativistic, because the Fermi momentum is comparable to this m naught c, and so that you can say that the electron will obey the relativistic mechanics, not the classical mechanics. So actually our calculation in this case is a remarkable combination of quantum mechanics, relativity and gravitational law. Okay? In fact, the Fermi gas possesses 0 point energy and enormous pressure P naught, which is balanced by the gravitational attraction. So first of all, let us calculate the properties of relativistic electron gas in its ground state, and for this we will first of all calculate the this inside pressure, which actually opposes the gravitational attraction. First of all, we are going to see it. Actually, for calculating this pressure P naught, first of all, we will calculate the energy of a single electron, you can see, by the relativistic energy momentum relation. You know, if epsilon is the energy of a single electron, okay, then according to Einstein's energy momentum relationship, you can see that epsilon is given as a square root of p square c square plus m naught square c4. This is the well known result, you know. Okay. Now after defining this energy, you can easily find the ground state energy of the Fermi gas. What will be this energy? You can see that this expression represents the energy of one of the electrons. Okay. So when you will sum up these energy of all the electrons having momentum whose magnitude is less or equal to the Fermi momentum, Pf is Fermi momentum, and add it, then you will get the total ground state energy. But you know, electron is a fermion, it has a spin half. So for getting the correct result, you must have to multiply this result by the number of quantum states, which has been denoted by the symbol Gs. So the ground state energy of Fermi gas is given as U naught equal to Gs times summation mod of P less or equal to Pf times a square root of P square C square plus M naught square C4. Okay. Now this Pf, which is Fermi momentum, momentum Pf is given by a square root of 2m epsilon, because that an epsilon, which is just kinetic energy, this is given by P square by 2m. So P will be given by a square root of 2me. And if you are talking about the Fermi momentum, then you have to take epsilon f, which is Fermi energy. Okay. But you have seen the expression for Fermi energy epsilon f is this much. This is h square over 2m times 3n over 8 pi whole to the power 2 by 3. Okay. So this is the value of Pf. After simplification, you can see that this Pf is given as this is h times 3n over 8 pi whole to the power 1 over 3. Okay. Now you have seen that this small n is capital N over V, which represents the number of electrons per unit volume. So instead of this small n, you can write capital N over V. Okay. So this is the expression for the Fermi momentum. Now we will see what will be the value of Gs. Actually, the energy distribution of electron is the energy levels of the electrons is actually so close that this summation will be actually changed into integration. So when you talk about the number of quantum states of electron having momentum between P and P plus dp, then that is equal to this G of P dp. Okay. This is actually the density of states. G of P is density of states. And we have learned several times earlier that this density of a state G of P is given as this much, 4 pi V over H cube times G times P squared dp. Okay, you have learned earlier. And this G, which is actually the degeneracy factor, this G is degeneracy factor, which is equal to 2s plus 1. So instead of this G, you can write 2s plus 1. So this is 2s plus 1 times 4 pi V over H cube P squared dp. But this degeneracy factor G small g is equal to 2s plus 1. And for electron, this spin is equal to 1 by 2. So 2s plus 1 will be 2. Therefore, Gs is given as 2 times 4 pi V over H cube times P squared dp. Okay. Now we will substitute this value of Gs in this equation 3. Okay. And this summation will be changed to integration, because the energy distribution is not discrete but almost continuous. Okay. And again, then you will get actually the ground state energy. Actually, the limits of integration will be what? For this, you have to think that the momentum cannot exceed this Fermi momentum. So the limits will be from 0 to Pf. Okay. So I have substituted the value of Gs here, and summation has been changed to integration, and your expression for U naught is like this. Okay. Now this 4 pi is a constant factor, so it has been taken outside of the integral. So U naught is given as 8 pi V over H cube times integral 0 to Pf. Now this M naught square C4, let us take it as a common factor, since this term is inside the square root. So when you will take it out, this term will become m naught c square. Okay, and inside the bracket there will be 1 plus p square over m naught square c square and whole to the power half. Okay, and this p square dp is at each. Okay, now for getting the value of this integral, let us put x equal to p over m naught c. Since x is equal to p over m naught c, so dx will be dp over m naught c. And from here you can see that this p will be equal to m naught cx. So now let us substitute this value, these values in equation 5. One thing, see about the limits of the integral. You can see from here that when this p is equal to 0, then what will be x? You can see x will be also 0. Okay, and let us take when p is equal to pf, then x will be equal to what? This will be equal to pf and divided by m naught c. And let us say this is equal to xf. We suppose that. So the limits has been changed to from pf to xf here. Okay, and all these substitutions has been made. So after making these substitutions, we get that u naught is equal to 8 pi v over h cube times integral 0 to xf m naught c square times 1 plus x square whole to the power half times m naught c x whole square times m naught c dx. You can see. Now this m naught cs, m naught, you can see this is actually there are 4 m naught. So m naught, there will be m naught 4, and there are 5 c, so that will be c5. So this expression is written as u naught equal to 8 pi v c over h cube times m naught c whole to the power 4 and times integral 0 to xf 1 plus x square whole to the power half x square dx. Okay. Now you can see the value of this definite integral will be definitely a function of xf because the lower limit is 0. So finally we will get an expression which will depend on xf. So instead of this integral, we have written here f of xf. Okay, and other factors are at each. Now let us see this f of xf. Let us simplify it. You know, f of xf has been written instead of this integral 0 to xf a square root of 1 plus x square dx. Okay. Actually, when this integral will be evaluated in two limiting conditions. First of all, we consider that this xf is much smaller than 1. When you say that xf is pf divided by m naught c. And if you say that this is much smaller than 1, it means pf is much smaller than m naught c. This is the case of non-relativistic motion. So when you consider the non-relativistic motion of the electron, then xf will be much smaller than 1. And in that condition, when you will make the binomial expansion of this and you will integrate, then you will get this much. This is 1 over 2 xf cube times 1 plus 3 over 10 xf square and so on. I have not done all the steps of this algebra, but you can do it. Okay. So actually in this condition, this function f of xf becomes this. But if you consider the extreme relativistic case, in the extreme relativistic case, the situation will be just reverse. XF will be much greater than 1. It means PF will be much greater than M naught C. In that condition, the value of this integral will be this much. This is 1 over 4 XF square times 1 plus XF to the power minus 2 plus so on. Okay? And you can see XF is this much. So in this way, we can see that F of XF has been obtained in two situations. Now let us substitute this value of function of XF in equation 6 to get the value of this ground state energy U naught. Okay? And after getting the value of U naught, now we can easily find the pressure, okay, which is exerted by the internal matter of the star P naught, and you know this pressure P is related to this internal energy by this relation. P naught is given as minus del U naught by del B. Okay, and U naught, you can see this is just except V, this is a constant factor. So 8 pi c over h cube times m naught c whole 4, this has been taken outside of the differential operator. And after that, there will be V times this x of this f of xf. There, this is just a product of V and f of xf. Okay, so we will use the rule of differentiation of product of two functions. So in first of all, we will differentiate V with respect to V, which will be 1. So the left term is f of xf. And after that, you will keep V at h and differentiate f of xf with respect to V. So first of all, this f of xf will be differentiated with respect to xf, and then xf will be differentiated with respect to V. Now put the value of this f of xf from this equation 7. When you will use this equation 7 here and simplify, then you get that this pressure is given as 8 pi c over h cube times m naught c whole 4 times 1 over 3 xf square plus times 1 plus xf square whole to the power half minus f of xf. Okay. Now xf has been defined, this has been defined here actually in two conditions. So when you will take xf is much smaller than 1, it means you are taking the non-relativistic situation, then this result becomes P naught equal to 8 pi c over h cube times m naught c whole 4 times xf square. But when you will consider the extreme relativistic situation, that is xf much greater than 1, then this expression becomes 2 pi c over h cube times m naught c whole 4 times x4 minus xf square. Okay. So in this way we get the expression for this pressure. Okay. Now our aim is to define the mass and density of this star 2, and for this let us consider that n be the number of free electrons in white dwarf star. Okay. So if n is the number of electrons, then you know the number of protons in this will be also n. Okay. And the number of neutrons will be almost equal to number of protons. So you can see that the number of nucleons in this star will be almost equal to 2n. Okay, 2n. Not almost, but exactly, because this is composed of helium, and in helium number of neutron and number of protons are same. Okay, so this will be just 2n. Now if you consider that m is mass of the star, v is its volume, then what will be its mass? since there are n electrons and mass of one electron, if you assume Me, then mass of the total electron will be n times Me. Since mass of a proton and a neutron are almost same, so we consider mass of a nucleon just equal to mass of a proton. Okay? And as the number of nucleon is 2n and mass of one of the nucleons is mp, so the total mass of the nucleons is 2n plus mp. And when you will add these two, you will get the total mass of the star. So mass of this star is given as n times me plus 2n times mp. You can take this n as a common factor, and so this is n times me plus 2mp. Okay? Now, since mass of an electron is much smaller, almost 1850 times smaller than mass of a proton, so for a time being we can neglect the mass of the electron, and you can say that mass of this star is almost equal to 2n times mp. Okay? 2n times mp. Now, if r is the radius of the star, then its volume is given as 4 by 3 pi r cube. Okay? And therefore, you can say that r is equal to 3b divided by 4 pi whole to the power 1 by 3. And therefore, from here, you can find the value of n. If you will evaluate n, you can see this n will be equal to m divided by 2mp. Okay? And therefore, now you can evaluate v by n. Why we are going to evaluate this? Because you have seen that in the expression of this internal energy, ground state energy, there was the factor v by n by v. So we can obtain the value of v by n. This is the expression for v, this is the expression for n. So you can see that this v by n is 8 by 3 pi times this much. Okay? Now you have seen the Fermi momentum Pf. We have obtained that this was h times cube root of 3n divided by 8 pi b. Now let us put the value of n by v from here. Here v by n is defined, so take its reciprocal. And you can see Pf will be h times 3 by 8 pi, this is at is. And instead of n by v, I have written this much from here, you can see. Okay? So after simplification, you can see that this is equal to Pf equal to 8h divided by 2 pi r times cube root of 9 pi by 8 m by mp. Okay? And therefore xf is Pf divided by m naught c. Okay? And Pf is this much, so let us substitute this value here. Now we write this expression in this particular manner. Instead of this expression, you can write m bar whole to the power 1 by 3, okay, whole to the power 1 by 3, see 1 by 3, and divided by r bar. Okay, here actually I have written this m bar instead of this much. This is 9 pi by 8 m over mp, and r bar has been written instead of this much, or you can see. Okay, so this is the expression for the xf, the value of xf. Okay. Now the enormous 0 point pressure is balanced by the gravitational attraction to bind the star. Okay. Actually, in the initial phase, the stars, you can think that these are gaseous material distributed in infinite region. Okay, so infinite diluteness is considered, and due to the gravitational attraction, these molecules of gas come together, are, are contracted, and finally a spherical celestial body of radius r is formed, which is called this star. So what will be the work done by the in against of the internal pressure in forming this star? You can see P naught is the internal pressure which opposes the contraction. So when you will take a thin shell of radius r and r plus dr, okay, so the work done in contraction in the contraction of radius from r plus dr to r, the work done will be P naught times 4 pi r square dr. P naught times 4 pi r square, this will be actually the force, and dr is just the elementary displacement. And when you will integrate this between the limits infinity to r, because initially this material was expanded in infinite region, then you will get the total work. So W is integral infinity to r P naught times 4 pi r square dr. Okay. Actually, this work done is stored in the star as the gravitational self energy. Okay. But you know, if r is the radius of a sphere and m is its mass, what is the expression for gravitational self energy? You have definitely studied gravitational self energy, electrostatic self energy for a spherical mass distribution, a spherical charge distribution. Since the attraction is attractive, so this gravitational self energy in this case is given as minus 3 by 5 gm square by r. Here m is mass and r is radius of the star. But this is nothing. This is the work done. This work done has been stored as potential energy. So you can equate this integral P naught times 4 pi r square dr from infinity to r by this. Okay. Now to get the result, let us differentiate this equation both sides with respect to r. With respect to capital R, we are going to differentiate it. When you will differentiate this LHS, this integral will cancel out. Okay. And instead of this small r, there will be capital R. Okay. And in RHS, the differential of 1 by r will be minus 1 by r square. So this minus minus will become plus. So you will see that this is P naught times 4 pi r square equal to 3 over 5 gm square by r square. Okay. And therefore, P naught is given like this. This is 3 over 20 pi times gm square by r4. In this way, we have obtained the expression for this internal pressure. Actually, this expression can be expressed in terms of this m, in terms of m bar and r bar. You have defined earlier m bar and r bar, and so this expression P naught, which have defined in 11, can be now written as P naught equal to 3 by 20 pi g, and instead of m, in terms of m bar, you can write this much, and instead of 1 by r4, 1 by r4, okay, you can write this much. This is r bar 4, okay. 2 pi m naught c over h whole 4 times 1 over r4. Okay. This is actually the value of equilibrium pressure. Okay. Now, when we actually use the extreme relativistic case which I have defined in equation 8, then you have seen that xf is much greater than 1. And then no white dwarf can have a mass greater than this much m naught, which is given as 8 by 9 pi times mp times 45 over 64 pi whole to the power 3 by 2 times hc by this much whole to the power 3 by 2. which is almost equal to 10 to the power 30 kg, which is the order of mass of the sun. And there actually, when we redefine this estimated value, actually m naught is correctly found 1.4 into 10 to the power 30 kg. Actually, this value is called Chandrasekhar limit. This is known as Chandrasekhar limit. Okay. So, according to this model, no star can become a white dwarf unless its mass is less than this Chandrasekhar limit. Okay. So, this is all about the theory of white dwarf, which we have seen just as an application of Fermi Dirac statistics. Okay. Thank you very much.